An enormous pleasure to welcome Mesfin Tsige to our seminar program. Mesfin did his undergraduate work in Addis Ababa in Ethiopia, and then he studied at the International Center for Theoretical Physics in Trieste in Italy. And then he got his splendid PhD right here at Case Western Reserve in 2001. Did a postdoc at Sandia National Laboratories, and then was an assistant and then associate professor at Southern Illinois University before being recruited away to the University of Akron in 2010. And he now leads a large group of about a dozen grad students, plus a postdoc or two at the College of Polymer Science and Polymer Engineering there. And I, of course, follow his publications, and I noticed a very interesting one on this topic of wetting. And so it seemed to me he's developing real insights into what is a very important phenomenon in many ways. So we look forward to your talk, Mesfin. And if people have questions, then please use the chat function to put them in, and questions of clarity we can interrupt Mesfin maybe for, but otherwise we'll leave the questions to the end. Okay, Mesfin.
Okay, thank you, Phil. Thank you, Shirley, for inviting me to present at the Condensed Matter seminar. It's really a great privilege to tell you part of the story, part of the research that we have been doing in my group in recent days. So I have two screens. I'll be looking this one, so you may be looking at the side of my face, but I'll try to look at the screen at times. In my group, we are using computational tools, especially molecular dynamic simulation, to understand mostly structure and dynamics of molecules at surface and interfaces. This could be small molecules, for example, like methane, CH4, on metallic surfaces, in this case, palladium, for tribology application, and also polymers. These are big molecules on surfaces and also interfaces. When it comes to small molecules, we immediately see aware structured ordering because these are small molecules. But when we get to polymers, I'm not sure how clear this is on your screen. What I'm showing over here is a few polystyrene molecules absorbed on a solid surface, taking different kind of conformation. And that is what pretty much complicates when we get to larger molecules like polymers and biological molecules, how they absorb at surface and interfaces. In our case, we also look at for applications. For example, I've been collaborating with an experimentalist that is looking for using carbon nanotubes for removing organic contaminants from water. The experimental indication is that carbon nanotubes can absorb or take away regular organic contaminants like trichloroethylene, trichlorobenzene, 2 orders of magnitude better than what we usually use, like sand. But they don't know what was going on. So we have done some molecular dynamic simulation to understand how those organic contaminants can actually absorb on the surface, and at the same time, what happens to water molecules. And we have expanded that investigation in terms of looking at membranes and so on. The story that I'm gonna tell you today, as Phil already pointed out, is wetting of surfaces, especially polymeric surfaces such as polystyrene. And the reason we focus on wetting is the way we usually characterize the surface of polymers is by looking at how they are interacting with water. With that, we say we have a hydrophobic surface or a hydrophilic surface. But in the process of characterizing their surfaces, we can also understand how the functional groups on the surface are actually responding. So when we bring a water droplet in contact with the surface, in general, if the contact angle is above 90 degrees, we call it bad wetting. When the contact angle is significantly below 90 degrees, around, let's say, 45 degrees, we say we have good wetting. And if the water droplet completely wets the surface, we call it complete wetting. all these are actually telling us different characteristics of the surface. So in our case, I have both a fundamental reason and a practical reason for why I have been focusing on understanding the weighting of surfaces. Let me see. From a fundamental point of view, long time ago, I was interested to find out what happens to a tiny film of water in the order of a few angstroms confined between two different surfaces. So what I'm showing you over here is we have a bilayer of water. This is a bilayer, which is about 5 angstrom. The benefit of simulation is that we can control how much quantity that we can have in our simulation. So I took a 5 angstrom, 2 layers, confine it in between. This is PDMS, polydimethylsiloxane, also a common polymer. It can be used as an elastomer and also used for contact lenses. And at the bottom, I have a solid substrate, quartz, which is also commonly used. And it is hydrophilic, which means it has, in this particular case, about 9.6 OH groups per nanometer squared on the surface. So I have hydrophilic, hydrophobic. When I contact and equilibrate the system, we see that the structure of the water has significantly changed. If I show you to close nearby, here I have the substrate. What happened is that the first layer close to the substrate is okay, but the second layer peels off and forms more like a hemispherical cup in between the PDMS and the alpha quartz. And this hemispherical cup would pretty much increase in size if I go from a bilayer to a trilayer. So we only have one stable layer, but the rest one will form a hemispherical cup. When we replaced the quartz with amorphous silica is what's commonly used for purifying water. And in that case, we have a small number of OH groups on the surface. Here I say 9.6. When we come to amorphous silica, I have about half or less, 4.1 to 4.3. So as a result, we have reduced the hydrophilicity of a surface. And combining the same bilayer of water molecule in between results into a spherical droplet. So all the water molecules spills off. It forms a nice droplet that's confined between the PDMS and the substrate. And this nanoscopic water droplet has characteristics completely different from bulk water. And this is pretty much what we usually encounter in many technological applications when we have confined water, both in biological and several other technological applications. And understanding the characteristics of water under confinement becomes important. In all these cases, the key is hydrogen bonding. What makes water unique compared to other solvents is the hydrogen bonding that exists in between water molecules. And I would like to remind you, because I'm gonna come back to this one later, when we talk about hydrogen bonding in ice, we have this tetrahedral structure, 4 hydrogen bondings per water molecule. When we go to a liquid state, we still have hydrogen bonding. Instead of 4, we get around 3.4, 3.5 on average. Of course, we have disordered water, but that hydrogen bonding is very critical. So every time when we look at the physical properties of water, we have to bring this hydrogen bonding into account. On the application side, of course, water has its own benefits and disadvantages. When we look at wind turbines in the summertime, we have difficulties because the ice forms on the surface that pretty much slows down all the operation. When we look at our airplane wings, we have the icing, which is always a challenge. We live in Cleveland. We know that they have to de-ice airplanes every time they take off. Now the question is, can we design smart surfaces such that we can actually delay ice formation? That corresponds to obviously changing the melting properties of water. And this has consequences in our environment. We know that our Earth is melting, the temperature is shifting, and that is adding more water to the ocean. And that's affecting the way we live. So we have a lot of challenges. And in all of this, the technological application has been, can we design smart surfaces? And of course, one of the things we always talk about is corrosion. This is $100 billion business. This corrosion has been a fundamental problem. And in most cases, the problem is that water molecules come in between. Let's say if this is our substrate, this was demonstrated through simulation some time back. If those water molecules penetrate through, this is just a cartoon representing the adhesive material, and then they come through and detach the bonding, mostly van der Waals bonding that's existing between the epoxy and the substrate. Other result, salt like sodium chloride and so on can diffuse into and result corrosion. So can we come up with ways of avoiding such kind of problems? So I look this both on the fundamental side and on the technology side and connect this back to hydrogen bonding. In the case of hydrogen bonding, if we come up with a mechanism of, let's say, increasing the hydrogen bond strengths, then that's going to increase the melting point. We really don't want to do that. But can we come up with ways in which we can actually make the hydrogen bonds slightly weak, which means decrease the melting temperature so that instead of melting at 0 degrees centigrade, can we shift it down to -5, -10 degrees centigrade? Those are the kind of surface we'll be looking at. In effect, what we know, if there was no hydrogen bonding at all, if we had a mechanism of turning the hydrogen bondings at all, the boiling point of water would be around -80 degrees centigrade, which means life wouldn't exist without hydrogen bond. Hydrogen bond is key for us to live on this earth. If we make it weak, of course, that would have been, life would have been at a lower temperature. No change means life exists as we know it. If we had make it stronger, then we could pretty much go to higher temperatures. So we connect all the properties of water with this hydrogen bonding. So in my case, I was really motivated by this experimental work that was published in 2011. The question they posed was, we have polystyrene, which is a common polymer. Polystyrene has a backbone of carbon, the usual organic molecule. It has a thin ring on the side. And this polystyrene, we find it in many different applications, mostly for packaging, because it's hydrophobic. So the question is, because it is cheap, can we expand its applicability, let's say for biomedical application, where we can grow cells? That means, can we make the surface somehow hydrophilic also? So they came up with a way of doing that. What they did was irradiating the surface of polystyrene with UVO treatments changes the surface from hydrophobic to hydrophilic. The way that's done is the ortho and para groups of polystyrene becomes oxidized. So oxygen-containing groups are tied to the thin rings, and that makes the polystyrene surface hydrophilic. And the benefit of this one is this change only happens in the top few nanometers. The rest of the polymer film doesn't change. Its mechanical properties, everything stayed the same, but the surface properties changes. As a result, they were able to twin from hydrophobic to hydrophilic, going down to a contact angle of around 46 degrees. Depending on how long they expose the surface to this UVO radiation, they can actually control the degree of oxidation, hence the hydrophilicity of the surface. So this is in a much controlled way. The way to think this is without changing roughness of the surface, because roughness has its own consequences on the contact angle, just only changing the chemistry and allowing the effect that we see is based on functional groups. And this obviously benefits us with the earlier fundamental question I talked about. Can I, continuously control the confining surface properties? And this pretty much gives us that option. The one challenge they had in their case was the large error bar in their data. That was very hard to avoid because you have a much larger surface, usually in the order of centimeters, and they are exposing that to UV radiation. So there could be different variation in the oxygen distribution on the surface. So when they put a water droplet, even if the average degree of oxidation is around 12, that water droplet could be on 12%, 14%, 15%. So when they take the average, they get larger fluctuation. And if they didn't have this last experimental data, it would have looked like as if it has saturated. But the last data point make them to conclude that there is a linear dependence. But this is more a hypothesis. In our case, we pretty much first simulated this experimental procedure. We have done the same approach. We took a polystyrene. This is a polystyrene film. All the details, each of the atoms, carbon and hydrogen, are included. And we have also characterized what kind of surface we have. That means when we do mapping where the top atoms are, this is a higher position, the blue is a shallow position, and we have observed a roughness of about 6 to 10 angstrom. This is more like doing AFM on the experimental side. Once we do that, we put our water droplet on the surface. So this is our polystyrene film. This is a water droplet. Each of the water molecules, some of them are evaporating, as you see. And because it is rough surface, you initially see that when it bounces, it rolls off a little bit because of the roughness of the surface. And finally, it settles down to a contact angle of about 95 or higher. So the benefit in our simulation is that we can follow how the contact angle is changing over time. This is more like a dynamic contact angle. And finally, when it saturates, we can go ahead and determine the contact angle. We can correlate that contact angle back to the interfacial tension between the liquid and the surface. And also we can calculate the work of adhesion with the information that we can gather. So we have varied the degree of oxidation of the surface as they have done in the experiments. In our case, we don't need to do UV radiation. What we do is we go and attach oxygen groups to a selected number of phenol rings. As a result, we can control the percentage, and we have measured how much the contact angle of water changes with the degree of oxidation. And we see a linear drop as already predicted by the experiments. The error bar in our case is within the size of the symbol. The reason being we have a better control in terms of the distribution of the oxygen containing groups on the surface. This is when we have 0%, when polystyrene is not oxidized. This is what I showed you earlier. We see that 95, 96 contact angle. Whereas when we oxidize the surface, now we see that the droplet is actually wetting the surface. We see a change to a contact angle of around 40, 45 degrees. So it is spreading, and at the same time diffusing. What we have done is we oxidized the phenyl groups in the top 2 nanometers of the film. And this orange that you see are the oxygens that are attached to the phenyl rings, and the red are the oxygen of water molecules. So there is diffusion to the top couple of nanometers and at the same time wetting. So the process is slightly complicated. You have a combination of different processes that are taking place. The advantage with the simulation is that since we know the position and velocity of the atoms as a function of time, we should be able to determine several physical properties of the system. So the first thing that we have done is to look at hydrogen bonding. When this water droplet is spreading, in the case of oxidized polystyrene, they are forming and breaking hydrogen bonding with the substrate, as well as the hydrogen bonding with their own. The lifetime of hydrogen bonding of water is in the order of 20 picoseconds. They have a very short lifetime, but a broken hydrogen bond lifetime is even shorter, in the order of 2 picoseconds. So they form and break very quickly. So how do we characterize hydrogen bonding? The usual approach is, if I have two water molecules, such that the oxygen of one water molecule is within a distance of 2.5 angstrom or less from another hydrogen atom of another water molecule, and the OHO of that one makes an angle greater than 120 degrees, we say they form hydrogen bonding. This is a geometric approach. There is a geometric approach and energetic approach. Both match very well. So we have followed all possible hydrogen bonding in our system. Here I'm showing you 3 representative cases. The red one shows the distance between O and H. The blue shows the angle. Let's say a water molecule coming in close proximity with a surface oxygen, but not within this geometric condition that we put. The distance is slightly above 2.5, while the angle is really 120 degrees. And this water molecule may occasionally form hydrogen bonding, but it breaks quickly. We have also other water molecules. They don't form, then form, break. That happens much faster than the 20 picosecond that I talked about. We have also water molecules. They form, break, and pretty much form again and stay for a long time. So we have a distribution of lifetime of hydrogen bondings that happen at the surface. But interestingly, once it reaches in equilibrium, the number of hydrogen bonding stays constant, stays fluctuating about a certain value. And when we look at that number of hydrogen bonding as a function of degree of oxidation, the degree of oxidation we talked about, we see this linear dependence. And that linear dependence, we believe, is the reason for the linear decrease we saw in the contact angle as we measure, as we change the degree of oxidation. Further, we have also looked at how many water molecules were forming hydrogen bonding with a given oxygen atom. For this particular case, for polystyrene oxidized, 99% of the time we have one hydrogen bonding between a water molecule and the substrate oxygen. We didn't see any multiple water molecule forming hydrogen bonding. If we had such a case, in the order of 50%, then we would have expected more like a quadratic dependence instead of a linear dependence. That would have also changed how the contact angle would have changed with the degree of oxidation. So that's a benefit that comes with the simulation, is that we can go ahead and gather those detailed information. Of course, the other interest is, let me see my screen, what happens to the hydrogen bond lengths? Because I told you about that changing the hydrogen bond length is key in terms of controlling its melting properties, dynamics, and so on. So what I'm showing you here is the hydrogen bond lengths between water and water molecules in the proximity of the surface and in the actual bulk water. This is what we see distribution. This is the probability of finding a water molecule, two water molecules within a distance of this much, OH distance. The green is the bulk. It shows the usual Gaussian behavior. And then when we look at near the surface, we see a similar Gaussian behavior. The location doesn't change much. The peak, it peaks around the same value. So we didn't observe much change. There could be slight changes, in how much the value would differ at higher ROH distance. But in general, we didn't see much observable dependence that would account for shifting the melting temperature. Whereas when we look at the distance between the hydrogen bonding of the water with the substrate, we tend to have a larger ROH value. So a water molecule has to break bonding with another water molecule to form a hydrogen bond with the substrate. So which means at least one part of the hydrogen bonding has shifted. That should have some consequences in the physical properties of the water close to the surface. Okay, so the story I told you so far is how we understand hydrogen bonding. Of course, we would like also to understand how these water molecules order on the surface. The one we have is a polymer surface, which tends to be usually rough. And we are looking at small water molecules. And the size of these small water molecules is much smaller than the roughness of our surface. So the question is, how are we going to characterize? So this is more of a technical detail, but I have to provide to avoid any confusion. The usual approach is we tend to use a slab approach, which means you take a slab, you count how many atoms you have, divided by the volume. That gives us a density. Let's say if this is my polymer, when I look at in that direction, I have a constant density. And when I reach to this, the surface part, there is a decrease in the density, more like tan hyperbolic. This is what's common in polymeric systems. The reason being, when I get closer to this one, I have areas I don't have polymer. So I end up dividing it by the same volume. And instead of dividing it only the volume taken by the polymer atoms or groups. So as a result, we see this kind of tan hyperbolic. We found that this hides most of the information that we need. The liquid-liquid community, however, have been using what's known as instantaneous interface approach. So what they have said is, instead of simply looking at a rigid coordinate system, take your surface of reference, the surface to be this surface instead of a plane. So that surface takes into account the roughness, and we look at the distribution of molecules with respect to this surface than with respect to a plane. When we do that, we actually start to see some of the molecular details. We observe ordering at the surface. That is what has been expected, but we were not able to first to see with this the slab approach. So we have looked at the density of water close to our polystyrene surface. The function of distance from the surface, 0 refers to the instantaneous surface I told you about. Every point has a 0 reference. What we see is a high density close to the surface. For historical reason, I have to say that there was a debate 8-10 years ago about the depletion region of water near hydrophobic surfaces. I think some researchers said there could be about 5 angstrom or a nanometer depletion region when we bring water in contact with hydrophobic surfaces. But others who used spectroscopy approaches, they say that's not true. And after back and forth, the community said the depletion region is not really possible, even close to hydrophobic surfaces. In our case, we don't see that too. At 0%, our surface is hydrophobic, and we pretty much see a high density of water nearby with no depletion compared to the oxidized surface. So this is 0%. This is as we increase the hydrophilicity, so less contact angle. Yes, we have higher density. More and more water molecules are absorbing on the surface, but we didn't observe any depletion region. And beyond 6 angstrom, we pretty much recover the bulk properties of water, which means the interface is actually affecting about 6 angstrom of water molecules from the interface. So we identify those water molecules within 6 angstrom as interfacial water molecules. With that interfacial approach, we are also characterizing the dynamics. If density is increasing with degree of oxidation, we should obviously expect that the dynamics should be decreasing. And that's what we have actually observed here. On this one, I'm showing the number of hydrogen bonding as a function of distance. This is the number of hydrogen bonding formed by water molecules with the substrate and among themselves. Of course, we see increase and finally more like saturation. And above 6 angstrom, we recover back to the bulk value. We characterized the dynamics in terms of the mean square displacement of these water molecules as a function of time. This is for the case of no oxidation, and the green one is when the surface is fully oxidized. So there is a significant drop in terms of the dynamics of the water molecules. On this one, I'm showing this is in bulk, the diffusion of water in bulk, which is about 2.5, the usual value of 2.5 times 10 to the power of minus 5 centimeters squared per second. And this one is in non-oxidized polystyrene. This is in highly oxidized polystyrene. So we see a significant change in terms of the dynamics. We also looked at the relaxation time, how the hydrogen bonds that form and break decay over time. This relaxation time is directly correlated with the lifetime of hydrogen bonding. So the way we do that is at a given time, we have a certain number of water molecules forming hydrogen bonding with the substrate. We follow them, how they form and break, and we generate this correlation. And that correlation decays exponentially, more like a stretched exponential. And from that, we extrapolate the relaxation time tau. And we actually determine that relaxation time as a function of distance from the substrate. We separate what happens to close to the surface. These are the interfacial water molecules, and away above 6 angstrom, which we said shows bulk kind of behavior. So what we have found is within 5 angstrom, we see an increase in the relaxation time of the hydrogen bonding. That means once they form hydrogen bonding, they tend to stay longer because this corresponds to the lifetime of hydrogen bonding. But when we go above 5 angstrom, we get into the bulk properties of water, and we don't see any dependence on degree of oxidation. So the effect of the substrate is limited within 5 to 6 angstrom, and that's what we actually observed from our relaxation data. So what we have observed in our case is there is a heterogeneous behavior in the hydrogen bonding at the interface. Heterogeneous in a sense is that this is a cartoon showing, let's say, this is our polystyrene surface. These are the oxygen part. And then we have water molecules. These are what we call interfacial water molecules. So a given water molecule, a given interfacial water molecule maybe either forms a hydrogen bonding with the substrate, or it may be forming a hydrogen bonding with another water molecule which forms hydrogen bonding with the substrate, or neither of the two. It will be interfacial, but not involved in any form of hydrogen bonding with the substrate. These three show a completely different behavior. And going forward, whenever you see OH, it implies a water molecule forming hydrogen bonding with the substrate. The green is indirectly connected with the substrate, whereas the blue means just interfacial, has nothing to do with any hydrogen bonding with the substrate. So we carefully characterized all these three different water molecules in terms of how they form and break hydrogen bonding with the substrate. The first thing that we have done is we looked at their diffusion coefficients, how the diffusion coefficient changes with the degree of oxidation. So in bulk, the diffusion coefficient is around 2.5. It's up in here. What we have observed is that all the interfacial water molecules have less, they move less than what they do in bulk. So there is a reduction in the diffusion coefficient. But there is also a difference between the three different kinds of water molecules. Those that are directly involved with hydrogen bonding with the substrate, they move slowly, they form and break. The other one tend to move slightly faster. But surprisingly, there seems to be a saturation in terms of the diffusion coefficient at around 0.07. When we map this back to the contact angle, it seems at around 45 degrees. So at a contact degree of 45 degrees, we see that the dependence pretty much changes and doesn't show any dependence thereafter. So we found this 45 degree to be very intriguing. I will explain to you in the next slide. We also looked at what happens to the relaxation time, which is the lifetime of hydrogen bonding. This is the blue one is for those interfacial water molecules not involved in hydrogen bonding with the substrate in any form. We didn't see any dependence on the substrate. Actually, we were surprised by this, and we wanted to look at, looking at other surfaces. We considered self-assembled monolayers, and both hydrogen terminated and H terminated. We found the same property around 6 picosecond. PMMA, polymethyl methacrylate, on those surfaces, we found the same thing. Even on other surfaces, we didn't see any change. And the conclusion we came up with is, if we have interfacial water molecules not involved in any form of hydrogen bonding with the substrate, they should have a universal lifetime of around 6 picoseconds. Whereas the other water molecules, either directly bonded or indirectly bonded, this is directly, indirectly, they show a dependence that changes the slope around the same contact angle of 45 degrees. What's critical about this 45 degrees is that the community has been also debating whether we can come up with a molecular level explanation of the transition from hydrophobic to hydrophilic transition. The usual definition is that if contact angle is above 90 degrees, we say hydrophobic, below 90 degrees hydrophilic, but there is no molecular level explanation of what's going on. And with that, a couple of groups from the simulation side, Garde's group from REPI, they showed in 2009 that when they calculate what they call the free energy of hydration of a hydrophobic solute near to the surface, by how much the free energy changes on the surface compared in bulk water, they see a negative value in the hydrophobic surfaces and a positive value in the hydrophilic surface. This is by varying the size of their solute. And what they have observed is that all of them cross at one particular point. And that particular point corresponds to a contact angle of around 45 degrees. So they came up with the conclusion that the definition of hydrophobic to hydrophilic transition should be really on a molecular level, should be 45 degrees should be the angle that we should be looking at instead of 90 degrees. This is pretty much from the simulation side. On the experimental side, my collaborator Ali Dunajwala from our department, he used some frequency generation approach where they monitored the freezing temperature change as a function of contact angle. So they have considered different kind of surfaces, sapphire and self-assembled monolayer. What they have observed is that there is a change above 54 degrees, above 54 degrees of contact angle. And in their case, what they have said that above 54 degrees, a strong some frequency generation peak associated with highly coordinated water seems to be forming. So highly coordinated water, that's key. Something is going on at the molecular scale. In our case, looking at the hydrogen bonded network, what we have found is that at this degree of oxidation, the water molecules forming hydrogen bonding with the substrate show some kind of percolation. If we look at them, there is some kind of percolation that's forming, and pretty much that happens around this value. Once that's achieved, then we don't pretty much see a change in terms of the diffusion coefficient and a few other properties. So we somehow correlate hydrophobic to hydrophilic transition to be directly correlated to the percolation of hydrogen bonded network on the surface. Well, the benefit from our simulation is that we can further go and explain why that happens. What we have done is we have calculated how these individual water molecules are interacting with the surface. So we determined the interaction energy as a function of degree of oxidation for the 3 different kind of water molecules. The free water molecules close to the surface, they have an interaction energy of in the order of 1 kilocalorie per mole, which means the dynamics of those water molecules really is controlled by thermal fluctuation. The substrates has nothing to do in terms of controlling their dynamics and lifetime. That's why we didn't see any dependence on the substrate type. Whereas the other water molecules, somehow observing the oxidation of the surface, they have interaction energy of 5, even to 10, 15 kilocalorie per mole, which is beyond thermal fluctuations. Pretty much they are bound to the substrate, and as a result, their dynamics and interfacial properties has been significantly changed. So this is what we have observed for the case of polymeric surfaces that show partial weighting. I know I'm getting closer to my time, but I would like also to tell you about what we have done for the case of atomically flat surfaces. That means surfaces that don't have roughness, highly oxidized, which shows complete weighting. And when we look at complete weighting, the weighting property is completely different. So in this particular case, what we have considered is the sapphire. Sapphire is aluminum oxide, the alpha form of aluminum oxide. It is used as a catalyst and also catalyst support, and even in some cases in microelectronic devices. So its interaction with water has been very important. When we put a water droplet on the surface, this is the sapphire surface. I'm not showing you the OH groups to avoid confusion with the spreading water. So when we bring this water on the surface, it is actually spreading. If I avoid the substrate, you could probably see it more clearly. So this water droplet is coming. I'm not showing you the substrate. Then you have this single monolayer coming out. This is what we call it a monolayer, a single monolayer. And then we have on top of that a hemispherical cup. So we have 2 different kind of dynamics going on at the same time. Digens actually, when he was studying weighting, he was characterizing this precursor film is what he called it, with a thickness of H in the order of nanometers. In the case of water spreading on this surface, in our case, what we have seen is just a monolayer Others think that maybe another layer may develop over time. In the droplets that we have investigated, we didn't see multiple layers coming out. We have only seen single layers. And we have done that for different kind of droplet sizes. And of course, in our case, we wanted to characterize the hemispherical cup sitting on top of the monolayer. And the way to do that is to map this to a density map. So we took this and looked at how the density of this water droplet changes over time. And of course, the benefit of this density map, so inside the water droplet, we get the usual 1 gram per centimeter cubic. At the interface, of course, it drops to around 0.5. These things going are water molecules evaporating from our droplet. And of course, some of the water molecules could come and absorb on the surface. That's what you see, these low density values. But the two areas to look at is this red high density region, that's a monolayer, and that monolayer is changing. In our case, we monitor its position. And of course, we also have this hemispherical cup, which is also changing. We monitor that with the green line. We also monitor the contact angle. So if I play this one again, the contact angle is changing, the height of the droplet is changing, the location of both monolayer and the hemispherical cup, all those quantities are changing over time. So we look at how all those things change with time. So in short, this is the picture we have. I have this monolayer, I have this spherical cup. We are measuring the monolayer from the center, and this bulk from the center again, the contact angle. For one particular droplet, this is what we see, which is common for all of them. This is what happens to the monolayer radius. We observed 2 different time scales. Initially looks faster and then it slows down. This is the bulk radius of the hemispherical cup. It initially increases, then decreases. So it initially expands, then starts to shrink, and finally disappears. This is the height, the green one. Initially decreases significantly, and then slowly decreases, similar to the bulk radius. The contact angle drops, but then it seems to stay constant around 20 degrees. What happens is that there is a significant change initially, then that hemispherical cup stays at a constant contact angle, but just keeps on shrinking. When we look at the monolayer radius as a function of time, of course, there will be dependence on the droplet size. We can actually come up with a universal behavior when we normalize that monolayer radius by the maximum monolayer radius. The maximum means when the droplet completely wets the surface, when it just completely becomes a complete monolayer, we call it that R max, and the time it takes to reach that point, we get this universal behavior, independent. So it becomes independent of our droplet size. And what we have observed is that this scales as t to the power of 1/5 at a later stage. This is very different from what has been predicted by theory, usually known as Tanner's law. Tanner's law pretty much says at a later stage, it should grow as t to the power of 1/10. What we have observed in our case is a much faster dynamics. It may have got to do the fact that we are taking molecular level information of what's happening, taking actual water molecules, and encouragingly, recent experimental results showed a similar behavior. Actually, the experiments, they found 1/4, t to the power of 1/4, a spreading of a water droplet on a textured surface. So their surface is slightly different. Yes, it is hydrophilic, completely wetting the surface, but slightly textured than our atomically flat surface. They found even a much faster dynamics than what was predicted by Tanner's law. The details of this recent work can be actually found in our recent publication. So to conclude my talk, pretty much, I think you may have seen that in the process of analyzing our simulation data, what we have done is similar to, let's say, for surface roughness. It is like using atomic force microscopy in the experiments, because we have characterized the roughness of our surface. And of course, we have also determined the glass transition temperature of our polystyrene film, because the polystyrene film that we had was in a glass state. It is similar to using differential scanning calorimetry in the experiments. We have also measured the contact angle, which is having optical or force tensiometer. We have measured the relaxation time. In experiments, you will need NMR or dielectric spectroscopy. We have also measured the lifetime of hydrogen bonding, which is similar to using IR or Raman or NMR. For measuring diffusion, you need dynamic like scattering. We have analyzed the surface properties. For example, you have to use some frequency generation or other spectroscopic approaches. All this is actually possible through our simulation approach, just by applying the statistical mechanics that we already know. And after combining all these different cases, we have observed longer lifetime of hydrogen bonding at interface than in bulk. The dynamics is much slower. And of course, we have observed a heterogeneous interfacial water properties at the interface. I would like also to thank funding the last several years from different sources. That has been very helpful in terms of executing most of the research work that we want. And also, I would like to thank my group members. This was taken recently, as you can see. We have put masks, but our social distancing is in the order of nanometers instead of feet. So, these are my group members. And of course, last but not least, I really would like to thank Philip Taylor for being a great mentor for me since graduate school. Thank you very much. Thank you.
Well, thank you very much indeed, Mesfin. It was a most informative talk, and thank you for your kind words at the end to fully reciprocated. I guess there's some questions appearing in the chat now. The first one from Will Grossman was concerned with texturing of the surface, and what are the choices that you make for that?
Oh, can you repeat, Phil, the question?
How do you, Professor Tsige, choose or deduce by simulation the initial surface roughness of the polystyrene substrate?
Oh, okay, very good. That's a very good question. So in our case, we don't choose what the surface roughness is. That is actually the result of the simulation. So in our case, in the kind of simulation that we do, this is pretty much doing the same experiment in the computer. The roughness is proportional to the temperature and also to the molecular weight of the polymer that we consider. In our case, we considered polystyrene of about 40 monomers. If we had taken a longer molecular weight, the roughness could have increased. And also, if we have increased the temperature, roughness would have increased. So in general, the roughness that we got in our case, it corresponds to the molecular weight and the temperature that we have worked at. We didn't control the roughness by hand. It is a result of the physical properties of that particular system.
Very good. So I can either read these questions in the chat function, or I can ask, say, Walter Lambrecht to unmute and ask his question if he would choose to.
Sure. Thank you, Mesfin.
Hi.
Nice talk.
Thank you.
So my question is sort of, how do I understand the hydrogen bonding at a quantum mechanical level? So usually it's described sort of as this interaction between the slightly negative oxygen on one molecule and a hydrogen, which is a little bit plus, and it seems like it's all just electrostatics. But
yes.
and sometimes I read it's dipole-dipole interaction, and I sort of wonder what is the current understanding of, if I'm doing a density functional theory calculation, am I getting the hydrogen bonding right or not? And how does it depend on, how do you build in these kind of features of the hydrogen bonding in your simulations to begin with? Because
Yes.
all the rest follows from that, right? You sort of study how it depends on the dynamics, and as I understand, how many molecules are close to each other and so, but what's the fundamental interaction? How well do we understand that?
Yeah, that's a very good question. Exactly. I think in our case, even the question at the beginning in the classical simulation community was, is it really appropriate to say that hydrogen bonding can be actually captured in a classical sense?
Mm-hmm.
Then the answer for that was yes, because 95% of this hydrogen bonding is electrostatic.
Mm-hmm.
Only maybe 5%, in the order of 5% is like covalent bonding, which means in our classical simulation, we can capture that 95% of hydrogen bonding through partial charges. So we have the oxygen of the water molecules negatively charged and the hydrogen atoms positively charged. So as a result, they form dipoles. So that dipole is correctly captured from the classical simulation of water.
Mm-hmm.
I have to mention that there are so many water models. It could be more than 50 or 60 water models that actually exist. Water turned out to be a very difficult molecule to simulate. The polymers are much easier than water actually. Because of its anomalous properties. When you bring them in bulk versus at interface, depending on what model used, you may find different properties. But the model that we have actually used, it's called TIP4P or SPCE. The two water models have been proven to work very well, both in terms of bulk and interfacial properties of water. So the answer to your question, yes, DFT, ab initio kind of calculation would be very helpful to capture those hydrogen bondings. But the fact that it is dominantly electrostatic, it can be captured through classical simulation like molecular dynamics.
Okay, thank you.
Thank you.
Chuck Rosenblatt, would you like to ask your question?
Sounds like one of those TV shows. Come on down.
Okay.
Yeah, the bane of experimentalists doing things like this are impurities that get into the system. So you had very nice polystyrene and you had very nice water. What about if there's crap in your system? Have you been able to model that?
Oh, say it again.
Pardon me, I should have given a trigger warning.
So
have you considered using a third component that might find its way to the surface through diffusion and create issues with your whole wetting model?
Yeah, so in our case, what we have done, as you said, is pure water on pure polystyrene. But others, let's say, who are interested in terms of nucleation and growth, how ice could form on a surface, they have actually included some kind of impurities. It's possible to include impurities in the water. In our case, for this particular case, the objective has been to see how weighting on a macro scale, even if we are doing nanoscale droplets, is to compare with macroscopic contact angle measurements. But others who are more focused on understanding what happens to the water molecules close to the surface as you cool down below room temperature, even getting closer to 0 degrees, and want to understand how crystallization might happen, they have included other impurities. Those impurities could be nucleation sites. So they wanted to know, are those responsible? Let's say you could have sodium and chlorine ions in the system. Those allows you to calculate the hydration shell, and you can monitor how that changes as you cool your system down and how it can actually crystallize. The answer to that is yes, it can be done, but in our particular case, our objective was not in that direction.
Very good. Okay, thanks.
Thank you.
As you mentioned the freezing topic, perhaps I could ask a question. your slide about freezing temperature, how do you define freezing at a surface?
Okay, so on the experimental side, so the simulation and definition from the experimental side could be different. Let's say on the experimental side, they sometimes characterize water being ice-like. They call it ice-like. When they say ice-like, it's more on the dynamics. When they don't see more motion and also slightly oriented dipoles. When the dipole moments orient in a certain direction, in liquid water, we don't have any preferable orientation. They cancel out with each other. But at the interface, there could be excess dipole moment orienting in a certain direction. They call that ice-like. So in our case, we follow that traditional definition of saying, okay, our water molecule behaves like ice-like because it's not like liquid water, to differentiate from the ideal properties of water in the usual bulk properties. Ice-like is not in a traditional sense of making for hydrogen bonding or forming a crystal. In the case of complete wetting, the monolayer that I was showing you on this one, in this particular case, the reason I say it is ice-like, you can actually see, if you look at it, the structure, we see a well-defined structural properties. This is ice in a dynamic sense. It's not a frozen ice. It's forming and breaking, but as a result, it has some structures. We see a well-defined structure going on. Dynamic-wise, no, it's not ice, it's moving, but structural-wise, it seems like ice-like. So the ice-like definition is interchangeably used, either characterizing the structure or the dynamics. If we see any of the two, we tend to associate like ice-like properties.
I see. Thank you very much. Sherry Heshuk had a number of issues to raise. I don't know if she would like to choose one of them.
Thank you, Philip. I'm calling in regards to first question. Would you include your link to the research paper? I'm trying to find the actual notation in the chat. So that takes care of that. And a question about industry application. When you don't have a perfect environment, like the one expressed here, what are the other factors besides cooling, temperature, perhaps impurities that might cause this to change or be, I guess, less conform?
So I think when it comes to application, I would like to actually point out that the usual approach of characterizing polymeric surfaces using a contact angle is not a good thing. I have a reason to say that. Because what we have observed is that depending on what kind of polymer system that you have, the functional groups on the surface could vary depending on to what liquid they come in contact with. The reason being, when we prepare polymer systems, they are usually close to air, in close proximity with air, which is hydrophobic. And if our polymeric system has both hydrophobic and hydrophilic groups, so in the process of making the film, mostly the hydrophobic groups come in contact with the surface. Now, when you put a water droplet on top of that surface, initially you get a higher contact angle, but over time, you start to see the contact angle decreasing, because what happens is that the hydrophilic groups start to orient to the surface because they see water is coming in contact, the hydrophobic groups avoid, and then you start the water droplet completely wetting the surface. Those functional changes at the surface is very critical in characterizing polymeric system. A good example would be polyurethanes. When they studied polyurethanes several years ago, they observed a very interesting mechanical properties. Then they said, oh, we can use it for implanting in our body, for knee surgery and so on. And when they did that, it actually disintegrated within 3 months. Their data in a lab showed a lifetime of 5 to 10 years, but unfortunately, when it was applied in a body, it lasted only for 3 months. The reason was that there was functional rearrangement. Our body is 75% water, and when you have that polyurethane with a hydrophilic and hydrophobic functional groups, they start to rotate, water starts to diffuse in, and it completely compromised its mechanical properties. So in general, when we get into application, it's not just simply a quick contact angle measurement. We have to actually look at, what are the hydrophobic and hydrophilic functional groups that we have, and how do they change on the surface. Some of them may be rearranging in the order of nanoseconds. Others do actually take seconds, even hours, depending on what we call their glass transition temperature. So it's not a very simple thing. One can quickly say, you have to expect these fundamental changes in a certain amount of time. It needs time, and we have to know the functional groups of our system. I made it long, but that's pretty much what we have observed over the years.
While you're on that topic, your initial remark about contact lenses and the need for those to be hydrophobic, that was a surprising to me. And I don't know if that's related to what you were just saying.
I think for PDMAs, they have PDMAs in contact lenses. And I'm not pretty much sure if their objective is to pretty much create a gap in such a way that moisture wouldn't get in and affect our eye. But in our case, we would like to have also moisture to go through around. I didn't carefully investigate why we have PDMAs in contact lenses and what would be the benefit. But I think I would suspect that controlling the moisture is key.
Very good. I'm not seeing other questions in the chat function. Does anybody else have any point to raise? Shule.
Yeah, I have one more. Maybe this is a naive question. Yeah, by any chance, the spin degree of freedom somehow can be taken into account? Because I just know that the hydrogen bonding, covalent bonding, right? The spin has to form a singlet state. So you have the covalent bonding. So in any case that this is needed to be taken into account, the spin degree of freedom.
Yeah, so in our case, we have no spin in this classical simulation. So we are approximating quantum phenomena in a classical sense. Mm-hmm. So which means we don't have electrons. We focus on the atoms, less on the electrons. Then when we focus on the atoms, we can say that they are big enough such that quantum effects are not important. Then we can look at those atoms and say they can be calculated through classical Newton's second law. And the only thing we are saying is what are the forces acting on each atom. And those forces come in the form of van der Waals interactions. And in the case of bonded atoms, through covalent. And that covalent bonding is approximated by harmonic kind of bonds. So we somehow capture those quantum properties through our classical model. So we get less worried about what kind of spin states that we have. If we are doing quantum, yes, that would be important. But what we have realized over many years of doing simulation on water is those kind of properties at the larger scale that we are looking at will not be important.
Okay, that's essentially the classical molecular dynamics.
Yes.
Thanks.
Thank you.
Very good. Well, if there are no further pressing questions, as it's 1:55, we'll close the formal part of this with a round of applause. And again,
Thank you everyone for coming. Thank you very much, Phil, Sholey, everyone again. Have a nice day.
Thank you. We'll stop the recording at this point then, but we'll be